Great. Okay, sorry about the little delay. So Matt was nice enough to do a screen capture, install a screen capture on the computer. So that will help out with having a much higher resolution when you guys turn into the videos that's online. Because otherwise, sometimes it's a little blurry on this screen to start off with, and then it gets blurrier by the time it gets to you through the videos online. So this is pure screen capture, so much higher resolution. All right, so for today, let me get my corner here. Okay, so for today we're going to cover parameterization and mesh control, and the example that we're going to use is a tuning fork. And a few other things that we're going to go over is look at how to do tables and also mode shapes for different structures. So the idea here is to model a tuning fork, and the tuning fork is actually quite a useful type of device. And the way it works is that you have these prongs here, and they vibrate back and forth like this, right? And the idea is you want something to have like a really sustained long vibration, and you do that with having symmetry here. So when this bends out, that bends out, and so you're going to have pretty much a neutral node here. So very little energy is being transferred down to the handle, so you can hold this thing and it doesn't really dampen out as much the vibration. Okay, and a lot of people use that to tune instruments, and it's also being used for gyros as well. So this is kind of interesting use of this. So they're actually using a tuning fork that's the size of a micro device, the MEMS size of devices. And so they get this thing vibrating back and forth like this. So it's vibrating back and forth, right? And then as this tuning fork structure rotates, there's something called the Coriolis force. And so the Coriolis force is really interesting. If you have something moving with a certain velocity in a rotating frame, it creates a force that's perpendicular to the movement. And so what happens is that you start exciting these orthogonal modes right here. So remember, it's moving back and forth like this, the mass of that. And then all of a sudden, if this whole thing is rotating, then it starts having a movement in that direction. And the amplitude of that movement allows you to determine the rotation rate. Okay, so here's the Coriolis force equation right here, where it's 2 times the mass of whatever your of the proof mass that's moving. Omega is the frequency of the structure that's rotating. So for example, on your phone here, you have a gyro on your phone, and well, it's not a really good gyro, but if you have like a really nice gyro on your phone, and if you rotate it fast or rotate it slow, it's able to determine how fast you're rotating that by using this equation right here. So it knows the velocity of this thing right here. The only unknown is omega. So it solves for omega. And of course, it integrates that. And if you integrate omega, then you get theta. And then it tells you exactly how much rotation you actually did. Okay. So yeah, the one on your phone is a little coarse. I mean, it can tell like if you're holding your phone like this or holding your phone like that, then it'll like switch. So like, but they have much better gyros that can do a lot more. You have them in your car. They help do manage your stable control. They have them in the little unmanned air vehicles, right? Here's one such device right here. This is actually a MEMS tuning fork type of gyro, right? It's made out of single crystal material, and it has some electrodes on this that's able to measure how it's vibrating and actually actuate it to get it moving in that direction. And then it's able to sense in the vertical direction. Okay, so some of the things that we'll look at today is we'll look at meshing control. So as you can see, this mesh right here is very different than this mesh. And after class, someone wanted, last time we met, someone wanted to know how to mesh different things together. For example, this problem happens a lot where, let's say, okay, here's a very simple example, but it's a really important example though. Okay, so let's say you have a nanowire, and let's anchor it right here. And your nanowire is able to vibrate in this direction, up and down like that, right? So it bends up, it bends down, bends up, and so that's like mode 1, okay? So your nanowire, it's really small. It has very little weight, and you can measure its resonant frequency. Now, if you're trying to make a sensor that can sense the weight of molecules, right? Let's say it's the coronavirus, I don't know. If you have something on here that will allow certain molecules to adsorb to the, if you have some type of material in here that allows certain molecules to adsorb onto the surface and not others, then what you can do is look at the resonant frequency, right, and then determine from that resonant frequency what is the mass that is attached. If you remember, the resonant frequency of things for mechanical structures is the stiffness divided by the mass. Well, if you adsorb some molecule in here, you'll have some little added mass onto that. Let's call that delta M. And so if everything is known and you're measuring that, then you can back out of it what this is. And then you can determine what type of molecule is on that nanowire, right? Well, so let's say you modeled that inside of COMSOL, and you wanted to say, well, I know the weight of maybe some type of molecule. I'm going to represent that weight as maybe, maybe you'll have some film on here, and maybe you'll have, some other thing that represents, I don't know, your molecule, right? Well, the thing with COMSOL when you're trying to mesh is this is a huge area to mesh, and this is a very small area to mesh. So what COMSOL will likely do is divide this up into many more elements than down here. And sometimes that's not really a good idea, especially if this film is extremely thin. And so there are ways around that where you can mesh this with, well, I don't want to draw a mesh there, but let's say you have a fine mesh here, and you want the mesh elements right here to match up with the elements here, and with the same type of size of mesh. I'm going to show you how to do that with this example. So you can see that here, right? A lot of is really busy here and here, but the mesh on this face inside of the material, that is, think of it as being extruded straight through here, and you're just taking slices, all the way throughout like that, because it's very uniform. So it's just taking that mesh, extruding it through in the Z direction, and then taking slices. Okay. Otherwise, it'll look kind of funny where the mesh here would be, it'll gradually go from a high density to a lower density, and meshing is an art that, and you can get different values depending on the type of mesh you're using. The mode that we're looking for is mode 3, and it's at 440 hertz. Okay, and so for those that are musically inclined, you'll recognize that as the frequency of what note is that? Yeah. A, exactly. The one by middle C. So that's the mode shape we're looking at. We're also going to look at different mode shapes too. So you'll see mode shape 1, 2, 3, all the way through 6. Okay, and if you want to verify your results, it's always good to have an analytical expression, right? So here's the analytical expression right here, where F is the frequency in hertz. R1 is shown here. So R1 is the major radius. You have a minor radius too. So that right here is a torus. And so when we model the torus, we're going to have, so it's going to have a minor radius of R2, and then a larger radius, major radius of R1. Let's say here's the center right here. Like that. And then this L right here, this length right here, is this length. Now LP is a length that goes from here to here. That's just L, right? And then you have this piece right here that goes from here and it attaches. Okay, so you know the circumference is 2 pi r, and that's basically a quarter of that. So that's where you end up with 1/2 pi r. Okay, so it's really just the length from here all the way until it attaches. That's what this LP is right there. So ascribe R2. This right here is a Young's modulus, and this is the material density. And we're going to use steel, but other materials are used. Quartz watches use something similar to that as well. Okay, so let's get started. So start up your COMSOL 5.5. Okay. Okay, so the first thing you do is go to Model Wizard, and this is going to be in 3D. Okay, so click 3D. The physics we're going to use for this is the built-in structural mechanics. So select that, and then wait a minute. Open up and click on Solid Mechanics, and then click Add. And a few seconds later, it should display down here. Okay. Then go to Study, and we're going to look at eigenfrequency. Okay. And then just click on eigenfrequency, and then select Done. Okay, so the first thing to do is let's start making our structure. So let me redraw the structure here. So it looks something like that, okay? So this right here is a cone. This right here is a torus. This right here is a cylinder. This right here is a sphere, okay? And this radius right here is R2. This radius right here, all on that way, this is all R1. This length right here will be our L. Yeah. Okay, so the first thing to do is let's start with the cone. So either you can right-click on Geometry and then select Cone right here, Or you could click geometry in the ribbon and select cone right here. And then that adds the cone to this piece right there. So let me make sure I printed it out too, giving you guys the right values. Okay, so for the bottom radius of the cone, so it has bottom radius and the height. Okay, so for the bottom radius, let's do R2 for the bottom radius. Well, we haven't defined R2 yet, but we'll do that right after we do this. And then for the height, let's just pick H2 for the height. Okay, we'll define that. And then for this piece right here, you can do it by angle or radius. And what I mean by that is for the cone is that you can say, because this is R2. We define it as R2. So if you do it by the radius, then what happens is that your ending radius right here, okay, well, say at top, but it doesn't matter. Okay. So you could do it by this. I guess we can call it R3. Or you could do it by angle, right? Where this goes down a certain height, and it's defined by that angle. So you can go out a wider angle, like that. Or you can go an inner angle, like this. Okay, so let's do it by angle instead of radius down there. So we're going to do it by angle, and we'll get rid of that and just call it like they're using 2 degrees. See, over here it has a units to the right, so that's 2 degrees. So so let's build that real quick. So let's go to parameters and define our parameters. So for R2, let's say R2 is 2.5 millimeters. So we want to put millimeters in brackets. Okay. For H2, let's call that, what are these for H2? Let's call that 2 centimeters. As you see here, I'm mixing the units here, but that's fine. There's also R1. So for R1, let's define that as 7.5 millimeters. 7.5 bracket millimeters. And also, there's also that L for the cylinder. So let's define that as 7.8 centimeters. 7.8 bracket centimeters. Okay. And we're going to parameterize one of these, right? You could parameterize any of these, but we're going to choose L to parameterize, and it'll do a sweep through these values right here. So now that we defined the parameters, now we can go back to cone, and at this point we should be able to build it. So there we go, right there. So that's the cone. And let me show you what happens if I change the angle. So let's change the angle to twice as much. Let's say 4 degrees, and I do build all. See that? So here's the bottom radius down here, which was R2, and here's is just the angle. In order to figure out this radius at the top, you have to do some math, right? Because we did it by angle instead of by radius. And if you did negative 4 degrees, it would flare out, right? You do negative 40, right? Let me zoom extents. So this right here is R2, right there. And this angle is 40 degrees, okay? But let's go back to 2. All right, now for the position of this thing, let's make the position, so for the X position, let's put R1 for the position, and we're going to do build all, and you can see how it shifts over. So if you look at the mouse, so if you look at the X right here, positive is in this direction. So you expect this whole thing to move in this direction right here. So let's try that. Yeah, and it did. Okay. So that's just the positioning of this thing for the handle, the cone. And for the axis right here, it's you want this along the Cartesian. So let's put this at -1 instead of 1. And what that does, it just flips it, right? So if you do build all, then it just flips it, okay? So instead of R2 being down here, now R2 is up here. So you just inverted the whole thing, okay? Just to give you an example for these other things, I could have built it along X, and I could have built it along X like that. I could have built it along Y like that, okay? Or you can do Cartesian, and you could do some angle like this. Let's say X is 1, Z is 1, and Y is 1, and that's like off at an angle, as you can see right here. See that? Okay, so let's just go back to Cartesian, and I had my Z at -1, and these were at 0. Okay, so that's the first thing. The next thing, let's do the sphere at the bottom there. That's the bottom part of the handle. So let's click sphere, or you can go to geometry and then click sphere right here. Either way is good. So for the radius of the sphere, let's choose, well, they have a value. They have 4e-3. It's like 0.4 centimeters. So that's for the radius. And at this point, you can just say build all. So there it goes right there. That's if we did not change the position of it. Okay, but we're going to change the position. So for the position of this, let's put in the X direction, let's have it go over R1 for the X position, just like we did with the cone, and do build all to see where that's at. So that's right there. It looks like a microphone or and then for the Z direction, here's what we want to do. We actually want this down here, okay? And this is the Z. So if you want it down in the Z direction, you have to make it negative. So what we're going to do is we're going to move it down negative. We're going to put parentheses here. Oops, I'm sorry, that's rotation. Z. Yeah, negative. And then we're going to put R1, right? So it's going to go down the distance of R1 radius, and it's also going to go down the distance of H1, or I mean H2, and the distance of R1. And then we could just say build all. Oops. I think this is supposed to be R2. Let me see this. No. Wait, so R1?
Isn't it R1 plus H2 plus 4 e minus 3?
Wait, yeah, so let's do H2 first. So we know that's going to go down H, right? And then we're going to do, we can add R1 onto that. Why is it too far? Yeah, there it goes. I just divided my R2 by half. But yeah, but I don't like this part right here, because if you can see, let me zoom in a little bit right here. You see that? That's not going to be good for meshing. You see how it's kind of like that? So you want it to be overlap. So let's do, you say R2 plus H2? Yeah, that's good. Sounds good to me. So RH are R2 plus H2. Yeah, that's good. Okay, so the next thing, let's do the torus. So I'm going to zoom extents out. And so now we're going to add the torus, which is right here. And for the torus, let's make the major axis is going to be R1, and the minor axis is R2. So the major axis R1, minor axis R2, and the revolution it's going to be just halfway around, so 180. And so let's build that. And we'll zoom out to look what that, see what that looks like. So it's in the wrong position right now, but and let's see how that let's change the angle to see how that torus is built. Okay, so let's say we just did like 10 degrees. So if we did 10 degrees and then clicked build all, you see how, you know, it's starting right here. So it builds a circle right here of radius R2, and then it starts sweeping out. Okay, so if we did 40 degrees, build all, sweeps out a little more, did 90, sweeps out more, and so we're going to 180. Okay, now for the axis, that was built around the z-axis right here, right? So the z-axis is out like that, and it's rotating around the z-axis like that. You could have rotated it around other axes too, like let's try x just for fun, right? Then it's rotating around the x-axis right here. See that? It's rotating around this x-axis. If we did the y-axis, it would rotate it around the y-axis, which is right here, right? So the y-axis is sticking, you know, out this way, and it's rotating around that way. Okay. So what we want to do is so let's have it rotate around the y-axis, and so let's do something interesting. Let's rotate this right with this key right here, this entry point. So if you rotate it, the whole thing will rotate all at once around y. So for example, if I rotate it by 30 degrees, look what happens to this. See how it's rotating like that? So if I rotate it by 60, I rotate like that. Okay. So let's go back to 0, and how should we rotate this? You guys see that negative 90? You guys see that? Negative 90? So if we're rotating at negative 90, then this is what we get. Which is, so this is the right positioning, right? I mean the right rotation, but we just need to position this on top of that. So let's go to our position up here, and for the position, we'll put R1 here for the X and build that. And I wonder why. It's quite odd. Yeah, so this needs to be positioned up too. So let's say R2. I mean, I'm sorry, R1 up. Yeah, there we go. So I have X2 is R1, and also, I'm sorry, Z is R1, and and X is R1. Okay, so how's everybody doing? Get to this part? Great. Okay, now let's do our cylinders. So cylinders are right here. Okay, so for our cylinders, what we want to do is, oh wait, actually it says here, before we do our cylinders, let's first combine this stuff. So let's not do our cylinders just yet. Let's go back to let's delete this. So if you add a cylinder, let's delete, because I want to try to keep it in order. So after you have that torus there and you built all, let's now do a Boolean operation and union this. So for Boolean, you select union, and we want to combine all this together. So so you want to unselect. So clear this right here, keep interior boundaries. So let me show you the interior boundaries. So if you click on this right here, if you hover over this, it says transparency. So if you click on transparency, then you can see what's going on inside. See that? And you want to combine everything together, but you want to get rid of these boundaries. If you have those boundaries in there, it creates boundaries for the mesh. So the mesh has to mesh around those boundaries. If you get rid of the interior boundaries, then it frees it up, and it'll free up some memory as well. Okay, so let's click on this and then go Control A to select all, and then it puts everything right here, right? If you didn't want to do Control A, you can click on each one of these with your mouse, one at a time. It'll do the same thing. Okay, so then say build all. And now you can see that those interior boundaries are gone, right? If you remember, this was a cylinder and it went in here and you had the cylinder part. Now that part is gone. No more boundaries of that. Same down here. Remember this had some overlap and that overlap is now gone. So now this is much easier to mesh. Okay. So now let's do the cylinder. So click on cylinder. And then for the radius, we're going to do the R2 for the radius. And for the height, we're going to choose L, because that's our parameter for height. And so let's say build all. And you can see where that's at. Right here. So we're going to have to like move that into position. So it looks like that needs to go up in the Z direction. It needs to go up by R1, it looks like. And then do build all. And so it fits perfectly. You go up by R1. Okay, and you can zoom out to see what that's like. So that's part of the piece right there. So now let's do a second cylinder. We could do this with a mirror, like we did a couple of lectures ago. But let's just do another cylinder. Or we could do it with copy too. So we could do copy, mirror, more than one way to do things a lot of times. So the radius was R2. The length was L. And then we could do our build objects, and it's right on top of that. So we're going to have to first move it over this direction, either move it up and over or over this direction. So this is just radius from here to here. So we're going to move it over to R1. So that's in the, let me get my bearings right. So that's going to be in a positive X direction. So I believe you put 2R1, 2 times R1 in the X. Let's see where that gets us. Right here, great. And then we're going to go in a positive Z direction by R1. Let's build that. So there we go. Okay. So the next thing we're going to do is, let's go to they have something in here where they tell us to ignore some virtual edges, but I think we can ignore ignore virtual edges. I mean, it does make the computation a little easier, but I think that's not necessary. So let's go to material next. So for material, it's right next to geometry up here. So click on the material tab, and then say add material. And once you click on add material, it should add this new window on the right hand side over here. Okay? And remember, all this does is just toggle this on and off. So if you click it again, it goes away. Click add material, it comes back. So the material, let's go to built-in materials, and we're going to go down to steel right here. So you double click on that, and now you have your steel.
So we need to unionize the.
Oh, after the cylinders?
Yeah.
Yeah. So, okay. So I guess the question is why, right? So the reason why you don't want to unionize those just yet, you don't want to create a union for those, is that you want the mesh here to be different than the mesh there, okay? And that's what I was saying before, how we're going to try to control the mesh along these cylinders, okay? So it's still going to treat it as one material, right? But we want to have better control of the mesh. And also, remember, in here, we remove those interior boundaries. This boundary right here, we want to keep it. And I'll show you in a second how we're going to mesh this little tiny boundary inside of here all alone. Then we're going to extrude that mesh up through the cylinder. So we need that boundary, so we don't want to get rid of that. But then again, you may ask, what if you unionize it but keep the interior boundaries? If you did that, I still think it will work. Yeah. Yeah. Okay, so everything is selected, which is great already. Okay, so and you can see here where this is the Young's modulus of steel, the density of steel, and other material properties. So that's done. So now let's go to the mesh. Okay, so let's go to mesh. Here's a tab for mesh, and mesh is already down here. So for mesh, what we're going to do is, so let's click on mesh, and we want to select physics controlled mesh, which it already is. And then on the element size, we want to select find. Okay, so just do that. Then here's what you do. You want to set up a mesh on that boundary right there. So here's what we'll do. We'll right click on mesh. We'll go to more options, and then we'll do free triangular. Okay? And then from that point right here, we want to select those two things. So let's zoom in here. Is this zoom box right there? Okay, we want to select those boundaries. So one way to select the boundaries, because remember that boundary is inside of here. So one way of doing that is if you go to Home and then you go to Windows, here's the windows right here. And then you go down to Selection List. You'll click here. So here's all of our boundaries. remember, this is the model builder window. We just left that. Here's the selection list. And it, as you can see, it's going through every single one of these. The one you want is that one. So 3 for me is this. It may be a different number for you, but it'll highlight it. Okay, so once you have that highlighted, you select add to section, this plus sign, and then you can see that 3 is added right to here. I forgot you guys can't see this. Okay. I did tell IT about this. They just haven't fixed it yet. I'll remind them again. Okay, so oh, you guys don't see any of my numbers over there. Wow. Okay, so I'm going to cycle through until the other one is selected. I hope I don't over oh, there it goes right here. So for me, it's 29. I'm going to add 29. Is it a different number for somebody else? It's also, oh, wow, awesome. Okay, sometimes it is. It's different in here in the instructions. Okay, so once those are selected, we'll say build selected. Okay, and as you can see, only the boundaries are meshed, and that's it. Only those boundaries are meshed. Okay, that's exactly what you want. And now this is really nice because what's going to happen is that the mesh that goes through here is going to match up with these lines, and the mesh that's in here will also match up with these lines. So this mesh and that mesh will coincide at that boundary perfectly. All right, so let's go back over to Model Builder. So that's the selection list. Go over to Model Builder. Back here again. Okay, so the next thing you want to do is to do the sweep. So go to Mesh, and then you can select Sweep here, or you can go to the ribbon above and go to Mesh and sweep right here. It says Sweep. So you add that, okay? And then what you want to do is select the domains that you want to sweep. So the only domains we want to sweep, remember you have two things, boundaries and domains. Okay, that's a boundary inside. The domain is all the cylinder. Okay, so we want to select domain here, and it opens up this window. And then we want to select this domain, that's 1, and select that domain right there, and that's 3. Okay? I'll wait till you guys get caught up with that. So the next thing you want to do, once you've selected your domains, then you want to do right click on sweep, and then do explain how you're going to distribute that. Okay, and that is another hierarchy right here. So for this, you want to, let's break it up into 50 pieces. Okay? We could do more, we could do less. But it's going to take this, extrude it, and chop it up into 50 pieces. So select build selected and see what that looks like. So it should look something like that. Let me zoom out. Okay? Now that's all meshed. And then that's what that mesh looks like. And if you zoom in at the top right here, you can see that this domain looks exactly like the domain below on the other end. Okay? And that's what you want. The only difference is that you have these cross sections between that. Okay? And again, it's very useful, like if you want to make a, some type of molecular sensor where you have different domain sizes, you'd use this method right here to mesh that a little better without using up all your memory. Okay, so now after you do that, then you go to mesh, and then you right click, and this time we're going to do free tetrahedral. And for this right here is how we're going to mesh the remaining. Okay, that's what it says remaining. So then you just do build all, and then everything else is filled in. So you see that? It didn't touch this at all. Because it says remaining, it only meshed whatever remains. So you can select which pieces get what type of mesh in your structure. Okay? And also, if you, let me zoom in right here to show you guys this. If you zoom in right here, you can see that it was a really good idea to get rid of those inner boundaries in there, because now you can see how the mesh quality looks like. It's pretty much uniform. So it's not like, it really has high density. If we would have left those things there, the mesh in here would be very high density. A lot of memory would be used unnecessarily. Okay. Yep.
I think I got a union without getting rid of those features.
Wait, what happened? You have a union without getting rid of features?
Okay, it was like you didn't hear about this check mark.
Okay, so all right, so now if we were not going to do a parametric sweep, we could just in there and just do compute, right? Once you mesh it, that's the next step, using the next step. But now what we want to do is a parametric sweep. So the next thing you want to do is let's go to study. You can go study right here, click on it, or you can just go right click on study down here, and we want to select parametric sweep. Okay, and it adds that. Okay. And so what we want to do here is we want to, see this plus button right here? You want to add a parameter, how you want to sweep it. Okay, so you click on that, and it drops down everything that we had created, all the parameters that we created. If we don't list them, they'll default to their regular values. If we click on it, like this time we'll click on L, it's going to redefine our L for us. It's going to ignore the L that we had, and it's going to have this new L that we are going to define here with a range, with a sweep over. Okay, so the range is going to be this. It's going to be range, R-A-N-G-E, and 0.078, comma, 1E negative 4, that's the resolution. Okay, that's the each step size is right there. And the final value, 0.0795. Okay, and then you end in parentheses. Okay. So the first value is 0.078. Comma, 1e negative 4, comma, 0.0795. All right, so now let's do this. So let's go to eigenfrequency right here. And for here, we want to have them show us several modes. And for those of you who aren't familiar with modes, think of like a guitar string or something. So let's say you have a string tied at both ends. Mode 1 is like this, and that's the mode shape it does. So this goes back and forth like that. Mode 2 looks like this, right? So it goes this, right? Mode 3, as you guessed, it has 3 humps. Mode 4 has 4 humps. and on. So we're gonna go all the way to mode 6. But that's just with like one type of beam structure, okay? If you have a 3-dimensional structure, your mode 1, 2, and 3 are gonna look really weird. Because you have that third dimension. So you're not constrained. And also if you have structures like this that have a couple of things, you're gonna get different modes there too. Right? So for example, you go out like this, back and forth, you go back and forth like this, right? You can, just some weird things can happen. Okay, so we're gonna click that on. The unit is in hertz. It says here, search for eigenfrequencies around something, and we're looking for A, which was 440 hertz. Okay? So that's what we're going to search for, kind of like know the frequency we're looking for. And now let's do this. Let's go to the wait, where's the show default solver? Oh. Okay, so we're done with that. So we're like in the default solver right here. What we want to do is yeah, so let's expand this. Okay, so where it says solution 1, expand that, and then click on eigenvalue solver 1 down here at the bottom. Click on that, and it'll pop this up. And for the tolerance, instead of 1e -6 is low for this, so let's increase it by 1,000. So let's say 1e -3. Okay. So that's the tolerance we're going to use here. And then you could just do compute. So you could use the equal sign right here, or you can go back and just, or you can use it right here. So either one. Okay, so now it's computing. And here's a measurement bar right here. Now remember, it's doing that sweep, right? From that 0.078 to 0.0795 at those small steps. And for each of those steps, it's changing the length of this. Right? So as it's changing the length, for every length it changes, it's computing the eigenfrequency, the resonant frequency, and also the mode shape. Every single one. Is anybody faster than me? My computer? You guys are done? Oh, okay. Okay, here we go. So I finally caught up with the rest of you guys with my solver. Okay, so now we're interested in the mode shape that's around a particular frequency, like well, this one. So 436 hertz is kind of close. Now, if we plot that, so here's a plot. So if you change something here, you plot it, and it'll show you what that looks like. So this is the default view right here. So you see how that looks right here? So that's that shape that we're talking about. Okay, but that's the shape at a length of 0.07. I mean 0.0795. I have all these other ones to choose from. For example, if I have a shorter length, let's go to that one, and then get one that's kind of close right here. That's what that looks like. So still the same kind of shape, but the thing is that it's not exactly the right frequency for mode 3 here. Or actually, yeah, these are imaginary right here. So what that probably means is that even though they're true mathematical values, you probably wouldn't be able to see this kind of frequency in reality, right? These ones are good. We can look at these other frequencies. Here's a higher frequency right here. If you do a plot here, I'll show you what that looks like. You see what I was talking about? You get this really weird shape where the whole thing is like going from side to side. Here's another one right here. Here's like a little twisty kind of one right here. See that? Okay, so let's look at how to do, look at the table view. Okay, so let's try this right here. Let's go to, so let's click on results, right? And then let's, I think I have to do it up here. Results, and where's global? Global evaluation, right here. Okay. And then here's our data table. So let's look at this solution number, this one down here, solution 2. Yeah, so the results, so we use the results tab right there. If you wanted to do a double, to use your model builder, you can do a right click on values right here, and here's your global evaluation right there too. Okay, so we did global evaluation, we went to global evaluation, and then for the data set we're interested in is this number 2 right there. And for the table columns, let's do inner solutions. Select that one. And then we'll go here and do a replace. And then go to solid mechanics, global, and frequency right here. Solid dot frequency right there. And then it should load it up right here. So that's the expression we're looking for. There's it's a huge amount of data and all kind of different variables in COMSOL. So you have to like dig in there and tell it which one you want to look at.
I don't have the table columns.
Oh, you don't have this?
That's not.
The data set. We only have the study 1, solution 1. The data set.
We don't have parameter selection in the table column.
Really? Is that with everyone? Wait, also, so some people have this and some people don't? Yeah. Wow. Huh? Yeah, they don't even have that. Yeah. Huh. Try solution 1. Does it pull it up with solution 1?
We only have 2 options under data.
And just, what, none in solution 1? Oh, great. Okay, so let me just show you how they do the table. So then you just do evaluate right there, and then it shows you like it's working on it. And then if you pull this up, you should see the table values. Okay, so here's all your data, and you can plot it all out if you like. But so this column right here are all the values of the parameter that is swept through, the length. Okay, and the next column is mode 1 frequencies. The next column, mode 2 frequencies, 3, 4, 5, and mode 6 frequency. So if we're looking at, for example, the one that's closest to 440 hertz, that's like right here. See that? That's like 440.13. That's good. And so it tells us that 0.0791 should be the length. I mean, if we want to build, that type of tuning fork to have that kind of fundamental frequency, then that should be the length of those two cylinders right there. Okay. Okay, so we're out of time here. Yeah, that's okay. Yeah, that's that's all this example shows right here. Okay. Yeah, so I think for you guys, wow. I guess running through it. Running through one more time might correct the problem. Because sometimes you'll get an error in COMSOL and you're not really sure like where it came from. Okay, but anyways, so that's all we have for today, you guys. All right, see you next Thursday.